Hi, welcome to the last week of process control. I've taken over again after Professor Costas. We're on lecture 10, MIMO systems, multiple input, multiple output systems. This lecture is going to be split into 3 mini lecture videos. The first one we're going to consider the systems, and then we're going to look at 2 ways of dealing with them. So first of all, I'll just take a look through the first pages of the handout that you've got. We're familiar with what a MIMO is. We've met these early on in our lectures, but since then most of the control that you've looked at is for single input, single output systems, as shown on the left there. Why? Because they're the easiest to analyze, they're more ideal, and so you can do interesting things, interesting ideas in how to control them without the complexity of all the interactions. But you know that most systems that we would deal with are actually multiple input, multiple output systems, where we have m inputs, n outputs, and we can construct a matrix array, a matrix equation to describe how the inputs and outputs are connected using a matrix G of all of the transfer functions between them. And we've talked about this specifically. I did it in one of the online classes, exploring why we can write it that way, why the fact that we're using linear equations that enables us to write out these interactions as simple relationships of input to output via a transfer function in the Laplace domain. This is the sort of thing that we saw early on. This is a reactor where we have a flow coming into it with a concentration and a temperature. It's jacketed, so there's Tc coming in, Tc coming out from the jacketed reactor. And then out of the reactor we have a new concentration and a new temperature. So the temperature and concentration will be changing. The reaction might be exothermic or endothermic. So our outputs are the Ca and T, the outlet stream. The inputs here are the Ca and T of the inlet stream, and then we've also got the temperature of the jacket as another input. So we've got 3 inputs, 2 outputs, and then these are connected by this matrix of transfer functions. That's the sort of thing that we've seen repeatedly, and so we want to have some idea of how to apply the control strategies we've learnt about. How can we apply them to a system like this with multiple inputs and multiple outputs? Now, looking at the system like this, immediately you think, where do I start? I know how to add a controller between an output and an input, but there are so many choices. Which one shall I do? Which is the best connection to make between an input or an output? Or indeed, should I be using multiple signals to inform how to operate the controller? Well, what we're going to do is only look at single connections between an output and an input. Multivariate control is where you're looking at lots of signals at the same time to work out how to control. We're not going to go into that into this course. That would be another level of complexity. So we're just going to focus on one input and one output being connected, but we still need to choose which are the best ones to go with, and we still need to understand what the impact of doing that is on the system where you have multiple inputs and multiple outputs. Once you've done that, how do you tune the controller in a scenario like that? Okay, so we're going to start off by just considering what we know about these systems already, to see what we can work out about how they're going to behave. And we're taking a simple 2x2 system in this case. 2 outputs, 2 inputs, and that's our matrix G11, G12, G21, G22. Those are the transfer functions that describe the relationships. So that's the system we're looking at. 2 inputs and 2 outputs. Okay, that's all straightforward. And we could write out those equations in full like that instead. So y1 is equal to g11 f1 g12 f2, and y2 is equal to g21 f1 g22 f2. Okay, you know that already. How are these things connected? Okay, we've got the characteristics of them, and we know that we can find all of these out. We can either find it out by writing down equations that describe the system and solving those equations and getting the simultaneous Laplace to take the Laplace transform, you get the simultaneous equations which you can solve to generate this matrix, or you can do experiments where you add a step change to one of the inputs and then look at what the transfer function is for the outputs respectively, and you do that to work through all the combinations. So we know that there are practical ways of getting that matrix, but we want to think about what happens now if we decide to make a control loop feedback on this. So let's say we're going to take our output y1, we feed it back via a comparator to y1 set point, and then we take that signal, put it through a controller GC1 in order to control our input F1, and then F2 as it was before. What's the effect of doing this going to be? So let's consider how we can analyze that. So let's consider the case where F2 is 0. What's the effect of this control loop going to be on the system? So if F2 is 0, we have these two elements of our system are 0, that's 0 and that's 0. So y1 is equal to g11 f1, y2 is equal to g21 f1. Okay. We can immediately write down our equation for y1. We've solved that loop numerous times. You write the equation as it follows its way around and then rearrange it to get it into this form. So y1 is equal to g11 gc1 divided by 1 plus g11 gc1, all multiplied by y1 set point. And so this is the transfer function now that describes the relationship between y1 and the set point. That's all well and good, and that's what we're used to. We're used to doing that, and then we're used to being able to decide the type of controller to use and the parameters in the controller to achieve the response that we want. So that's the bit that we want to happen. But consider this, y2 is also a function of f1 via g21. So let's look at what happens to that. What's the impact of adding the controller to y2? We can write from our first equation, we can write an expression for f1. So f1 is equal to y1 over g11. We have this expression here, y2 is equal to g21 times f1. Substitute in for f1, so y2 is equal to g21 y1 divided by g11. And then we can substitute in for y1 to get our expression. So y2 is also affected by the set point signal, and it's affected by this transfer function. The g11s cancel, so we have g21 gc1 divided by 1 plus g11 gc1. And so that's the effect that we don't want to have. This is the effect we do want to have of our controller. Our controller is enabling y1 to be controlled by a set point, but the effect of doing that on the overall process is that y2 is going to be affected too. And it's affected by the controller, GC1 here. So the process of adding a controller means we've now coupled this one to this one. And that's something we don't want. We're just trying to focus on getting this to do what we want it to do. But in the process of doing that, we've inadvertently altered the rest of the system as well. So we need to be aware of that. We need to be aware that if we're adding a control loop, then that's not just going to affect the input and output you're focusing on, it's going to affect all of the other outputs as well. So what do we do about that? That's the problem that we're going to look at over this lecture. We're going to look at the different strategies for how you can tackle that situation. Okay, so this is showing the situation we were talking about, where we have our connections via the transfer functions between the two inputs and the two outputs, and we wrote down those equations. We've considered one closed loop so far. You can close both loops as well. So with one closed loop, this is what we've had. And as we pointed out, as we change the Y1 set point, that also changes G2. And so that's the problem. And in particular, if you put then some sort of aggressive controller GC1 onto Y1, then that will have significant effects on Y2. If we close both loops, of course, this problem is accentuated, and then the reciprocal is true, that now Y2 is going to be affecting Y1 as well. So it's coupled both ways. And that's just for a two input, two output system. You can imagine that if you have more inputs and more outputs, then obviously the number of internet connections increases rapidly, and it gets out of hand. And what will happen in practical terms, if you're doing some regulatory action for one loop, so if you're controlling one output in one loop, that's going to affect all the other ones, all the other outputs. And so what's going to happen then? Well, their controllers are going to start activating too. And so their controllers are going to respond, trying to make those outputs behave the way they are meant to. And then the process of doing that will affect the original one as well. So they're all coupled. So if one thing changes, they all change, and they all start working against each other. One tries to change it one way, another will try to change it back again. And so we have a bad situation. We've got controllers working against each other. That's going to give rise to unpredictable behavior, instability, and poor operation. So we can't afford to just do that blindly. We need to have some thoughtful approach to how we can minimize those effects and make them manageable. And there are three ways in which we can try and tackle this, or it might be tackled. And that's what we're going to look at over the remaining lectures here. The first way, I'll just say it because it's trivial, is that the first way it can be dealt with, if G12 and G21 are equal to 0, then of course we don't have a problem. So if they're equal to 0, we don't have any interaction between the F1 input and the Y2 output, for example. And so effectively then we just have two parallel single input, single output processes. So of course that's the simplest scenario, that if we happen to have those characteristics for our system, or at least if we can approximate that that's what we have, then that makes the control problem simpler, and we can apply what we already know without having to think about the interactions. What we're going to do in the next lecture is look at relative gain array. So this is the second way that we can try and deal with it. And this is where we assess the relative significance of the different combinations of inputs and outputs to work out which are actually the best ones to try and use to control and which are the ones that we have to avoid. So we'll pick that up in the second lecture. Thank you.